doing this. The first time was with Mikara. You know Mikara, right?
Yeah. I've seen that presentation on validator privacy, I think it was.
Yeah. Mikara, she did a talk with us in May. And then Cayman from Lodestar, he also did a talk. And then Vitalik, of course.
I came last week. I was looking at the talk last week.
Yeah.
Away, and I forgot the name of the other two. Ping Chen?
I think it's Ping Chen.
Ping Chen.
Yes. Yeah.
My Mandarin is not as good as Vitalik's.
It's all right. Like a lot of people don't know how to say my name.
Yahsin?
Yahsin, yeah. And so like the robust incentives group is mostly in Singapore, is that correct or no?
Yeah, I mean it's mostly me.
And who's Fred, you said?
Yeah, so Fred is somebody who I've been starting to work with for maybe about a month. We've been in touch. He's been working on like simulations and agent-based models as well. And we've been in touch for longer than a month, but I think we really started working together since a month. Yeah.
And he's not in Singapore?
No. He's in London, I think. And he's doing that part-time as well, so it's not like...
So it's basically you and a little bit of Fred.
Yeah, I mean, yeah. But I still work with like Danny. I work with Georgios, my advisor, right? So it's just I work with Vitalik. Vitalik is in Singapore, as you know. Yeah. So
are we allowed to visit Singapore? Do you think?
I don't think so, but they recently said that maybe we will do like a travel bubble between Hong Kong and Singapore. So I imagine, Taiwan is probably on the list soon after. I hope.
I hope so too.
Yeah. I miss good bubble tea.
He misses bubble tea. Are we?
Yeah, so the sound is good.
Okay.
Cool.
Already live right now?
Yeah, live. I shared the link to you. Let me. Can check that.
Okay, I'm gonna check it right now. This one.
Yeah.
And then
this is the link that's.
Should I just post it again? No.
Let me check. Let me check if the.
Okay, I'm gonna check it.需要再 po 一次吗？这是你刚刚给我的链接。不用。Okay. Should I give this link to Barnabé?
Yeah.
Okay. This is the YouTube live stream link.
I was looking at it actually. It looks clear. Yes, 3 people are watching now. I think it's the 3 of us.
That's 3 of us.
cache. Oh, you can't. Wait, can we say something?
I can say something. Sure.
Because someone chat box.
They can't hear anything? Okay, so I'm gonna say the name of the event. Is that all right? Yeah, so Taipei Ethereum Meetup is about to start in a few minutes. The topic is going to be about Ethereum Improvement Proposal, EIP 1559, gas golfing, and more. We are about to start. I'm just waiting for my producer, CC, is testing the audio for us right now.
So they reply they can't hear us.
Okay. That's perfect. I think somebody said they can hear us perfectly. So I have this microphone, and I hope it's on my side and like working well. Barnabé also has a super cool microphone. So we are going to start, right? Let's see, is that all right? Okay. Hello. Hello, everyone. I'm Yahsin. I'm your host. So welcome to Taipei Ethereum Meetup. It's our fourth time doing this online meetup, and I'm very excited to have guests today. So we have two guests. We have Barnabé from Singapore and Europe, and CC is from Taiwan. So we have two presentations. And what we're going to do is we'll let Barnabé to go first, and then we do a little discussion like Q&A, and then we'll let Chih-Cheng Liang go next. So everybody ready? So today I'm very excited to have Barnabé Monnot. He's the research scientist at Robust Incentives Group of Ethereum Foundation, currently in Singapore, and working closely with Danny and Vitalik and Fred and all of these really cool people and Georgia. And so today he's going to be talking about EIP 1559. It's one of the most significant change to protocol economics since Genesis, and it's one of the most popular and like most talked about topics for this year. And so please join me in welcoming Barnabé.
I should unmute. Thank you, Yahsin. Should I start sharing now? So. All right, can you see it?
Yes. Yes, perfect.
And the laser pointer. Yeah, thank you. Yeah, I'm very happy to be presenting at the Eth Taipei meetup. Today I'm planning to talk a bit about 1559. I know there was actually a presentation, a very good presentation at Eth Taipei on the same topic just a few weeks ago by Dominic, the Diode CEO. So I'm planning to tackle a bit of a different angle. I'm still going to explain, let's say, the basics of EIP 1559, just so that we're all on the same page. But I'll try to dig a bit deeper in the economics and some issues that the, let's say, proposal presents. And stop me anytime if there's any question. I'm monitoring the chat as well. And I think Yahsin is too, so yeah. But hopefully it's not too difficult. And I'll try to leave time for questions at the end as well. All right, so I first want to frame the problem, so the setting that we are looking at. EIP 1559 is an Ethereum Improvement Proposal, which purports to change the current fee market. So the fee market is what we call the idea that users who are interacting with the blockchain, they want to send their transactions. So they use, for instance, MetaMask. These transactions are the unit where something happens. So that's how you write stuff on the blockchain. That's how you get code executed. And it's a market because the blockchain, Ethereum, any blockchain, the space is limited. Like you don't have as much bandwidth or as much throughput as you want. So it's a market because if we have scarce resource, which is space, computation, that means that we need to find some way to allocate this space. And the way we have currently is what we call a first price auction. So I'm assuming here that, let's say, all users have identical transactions. So you can think of it as just a simple payment, for instance. And each user is attaching a bid to their transaction. So this user is saying, okay, I'm willing to pay 20 Gwei for this transaction to get in. This one says 30, this one says 40. And so these users kind of declare how much they're willing to pay for the transaction to be included. And then in the second step, the miners, which are here, they get to decide which transactions they want to include. And in the current system, the miners are getting the fees from the user. So in this example, I'm assuming that a block is very small and it can only hold 2 transactions. We would have a lot of problems if that was true, but this is just for this example. And so if you only have 2 spots and you have 3 users, as a miner, you want to pick the 2 users which have the highest bid. So I'm going to pick the one who declares 30 and the one who declares 40. And I'm going to make my block and add my block to the chain. So this is, let's say, the current setting that we have. So users are bidding, they announce their price, and the miners decide based on who has the top bids, who gets to go in a block. This is a bit, it's not very optimal. It's actually quite inefficient. So in game theory, in particular in algorithmic game theory, which is this subfield of game theory, which deals really with how computationally difficult it is to run, let's say, a mechanism, we kind of know that these first price auctions are not great because they're not very strategically easy. Like you tend to be bidding against other people versus a different mechanism where you would just announce how much you are willing to pay for a transaction. That's rarely what you do when you're bidding for your transaction to be on Ethereum. What you usually do is you check what is the current level of prices, and you just go ahead and set the price that you think will get you in. So it's quite difficult, like, to know, well, what should be like the price to get in. So I took this. I don't know if you have this TV show in Taiwan. We used to have a French equivalent.
Which one?
The Price is Right. Do you know this one?
Oh.
No? Okay. Yeah, in French, in French it was called le juste prix, the correct price. So yeah, so here the price is not right. So what I'm picturing in this slide, I took all the blocks of the week of September 20th, 2020, so just like a month ago, and I measure the ratio between the transaction that has the lowest price and the transaction that has the highest price. And you see that, well, for most blocks, this ratio is under 10. So it means that the difference between the lowest price transaction and the highest price is like 10 times. It's already not great. You even have blocks where this ratio is much, much greater. So you have blocks where one transaction gets in at 1,000 Gwei and the other one gets in at 1 Gwei. So you really have like this large, let's say, variance between the transactions that get in a block. And the reason why you have this variance is because it's just so difficult to guess what the correct price is. Like, what is the price that really gets me into this block? And so 1559, which is a proposal to change this mechanism, it tries to create a mechanism that tells you what the correct price is. And this correct price is what we call base fee. And I'll give a bit more details in the talk about this base fee. But the dynamics are actually fairly simple. So before we had a block, we considered that the block is full when, let's say, it has, so currently blocks have a limit of 12.5 million gas. So the block is full whenever you reach that limit. Now we say, okay, we're actually targeting a block size of 12.5 million gas. but we allow the block to be sometimes twice as full as that. So we have a target size, but the actual limit is twice that target. And we have this base fee, which is a price, like in Gui, and the base fee increases whenever blocks are too full. So when you're presented with a block that has, let's say, a gas weight greater than this target, you increase the base fee. And when you are presented with a block which is too empty, under full or below target, you decrease the base fee. So it's really like a market, supply and demand, right? When you have a lot of demand, you start increasing the price. When you have like lower demand, you decrease the price. So you can really think of this base fee as an entry price. Okay, does that make sense?
Yeah. So the base fee is basically new to the 1559, is that correct?
Correct, yeah. So there's no equivalent of base fee currently. What people usually use as the entry price, it will be something like the Eth gas station or the gas oracles that kind of tell you, oh, I've seen in the last 200 blocks, these transactions at 40 GUE, they've got in like within 3 minutes. So this is what you should say, but we don't have this kind of objective price, which is really based on the level of demand.
Yeah, and then you said it's dynamic, and this is the key characteristic to it.
Correct. So yeah, so base fee is actually moving every block. So I will explain a bit the dynamics, but it's you get it at the end of, after one block, it's set to some value. You look at the next block. If the block is too full, you increase the base fee, and if the block is too empty, you decrease the base fee. So it keeps moving around.
Yeah.
But we'll see that maybe not
fixed price. Yeah.
It's not fixed. Yeah, it's dynamic. So it's a dynamic, objective price for the transactions.
Yeah.
Yeah. So in this system, so we have a base fee, which is kind of given to the user, but the user still has to specify two parameters when they form their transaction. The first parameter is we still have this idea of a tip. So in the previous system, we have the bid, which is what the user is giving to the miner. In this system, the base fee is actually burnt. So, sorry, I should backtrack a bit. So in this system, the actual level of your transaction, you have to pay at least the base fee, but you can pay a little more than the base fee if you want to. And this is what we call the tip. So you can set a premium. You say, this is the maximum amount I'm willing to give a miner. So for instance, the base fee is 10, and you say, I'm willing to give also 1 GUE to the miner to compensate the miner for the extra work of including that transaction. And so now you will pay 10 plus 1, you will pay 11 GUE. And so the base fee is burnt, and this is for actually game theoretic reason. Otherwise, the miner could game the level of the base fee. I'm not going to go into that here. But the miner tip is what the miner actually receives. So this is what is helpful to determine who gets in. So much like the bids in the previous system, the miner is able to order the transactions based on this tip. And so, of course, you might not be getting in at the exact moment that you send the transaction. And so you also specify a fee cap. So you say, okay, if base fee raises by too much, then I'm not willing to pay this much. So you say, right now the base fee maybe is at 10 GUE. If it goes above 50 GUE, then I'm not interested anymore. So you specify the fee cap. And very likely, I'll come back to that at the end, but very likely these are values that we can set for the user in a principled and reasonable manner as well. So, but natively the transactions have these two parameters, whereas transactions in the current system only have one parameter, which is the gas price, so your bid. Does it make sense?
CC, does it
make sense to me?
Okay, great.
Yeah.
Awesome. All right, so I've been like looking at the dynamics of this base fee in, let's say, different situations. I'm giving a link in the slides. I can also link the slides after the talk in the chat. But the simulations are I'm trying to understand like what are the dynamics of a base fee. So if you have people transacting with it, like what should you expect the base fee to do? And so the simplest model you can have is a model where users come in, like between two blocks, you have a certain amount of users, more users, like a greater demand than the block can accommodate. But each step you have, on average, the same number of users. And the users have different values for their transactions. So some of them, they are very interested to have their transaction going. Some of them not that interested. But we always draw the users from the same distribution. So it's random, but it's always the same kind of users that come step after step. And so I start the base fee at a level which is kind of low. I just started at 1 GUI. But I have some users which would be willing to pay maybe 15 or 20 GUI to get into the block, because that's how much they care for the transaction. And so what you see is that at the very beginning, since the base fee is quite low, all of these users, they can go in. But after a while, base fee, it keeps increasing because there is a lot of demand and the users can still get into the block. The base fee is not pricing them out. After a while, the base fee gets like to this very high level and starts decreasing until it gets to the right, like let's say to the correct entry price. Okay, so this is a stationary environment because you have kind of the same users coming time and time again. So we should expect, of course, in a real environment that it should fluctuate a bit more. But this is a good benchmark case to see already that in these stationary conditions, the base fee stabilizes fairly fast. So we call that price discovery. So the base fee is really discovering the price at which the supply and the demand are equalized.
This is the simulation that you mentioned in the notebook?
Yes. I have a link here. Should I give you the slides now? Maybe I give it at the end.
Yeah, at the end.
I post the link. So what you see here is really this phenomenon of price discovery. So base fee is getting to the level where it prices correctly to equalize with supply and with demand. Okay.
Yeah.
And so, all right. And so I take the same simulation, but now what I actually noticed at the very beginning in the previous simulation, is my users are quite dumb. Like they say, okay, I look at the base fee and I'll give you 1 extra GUI for the miner premium. And so that's how I make my bid. But if I'm a smart user, and let's say I'm here, I might want to get ahead of everyone else. Like maybe I value my transaction 15 GUI. Like for me, it's that much I care about it. And so I really want to get in before everyone else. So I don't want to be priced out at the beginning. Or maybe I value my transaction 10 GUI, and I know that the base fee is going to be too high at the end. And so I should get ahead at the start, right? And so now I have strategic users. And so my strategic user is a user that is going to try and bid just above what the non-strategic users are bidding. So the non-strategic users are always setting their premium to 1 GUI, and they might get in or they might not. But the strategic user is going to look at, oh, in the previous block, what were the users doing? And let me do like just a little bit above that, right? So kind of in the system we have currently, where you're bidding against the other users. And so what we find here is that you can see the tips. It's kind of slight, but it's not a very long simulation. You can see that the tips in the blocks are actually increasing compared to here. Because now the strategic users, they try to get ahead and they try to do that. And this is something that we...
Yeah, the strategic users are basically the smart ones. So they want to get ahead of everyone else.
Exactly.
Did you get it?
So can I ask again, what's the y-axis?
The y-axis is the price in GUI.
Oh, I see.
So, yeah, the blue line is the base fee. So that's the level of the base fee. And the orange line is the tips. So the premium that is included in them. So what the miner receives.
I see.
Yeah.
Thank you.
So, yeah. And so actually what we sometimes hear as, let's say, a criticism of 1559 is people are saying, well, 1559 is not going to change anything, right? I still have the incentive to go ahead and set my bid to be just above the other users so that I can get in. But actually, that's not true all the time. And we find that after the base fee has stabilized, so here I picture it's the same x-axis, so the time steps of the simulation. I picture how many strategic and non-strategic users get in. And so at the very beginning, you see that, yes, strategic users are getting in large numbers. After a while, there's some kind of flip, and this is due to the pool, the transaction pool. I'm not going to get into that. But what you see at the end is that the same amount of strategic and non-strategic users get in. Because once the base fee has finished the price discovery, and once the price is correct for the current demand, you don't really have an incentive to be strategic anymore, because you know there is space in the block, so you don't really need to compete with the tip. And so when people are saying that it's never going to be you pay the base fee plus like a fixed tip, and you're always going to be competing with others, it's most likely not true most of the time. It might only be true when you have when the base fee is doing the price discovery. So when the demand is changing and changing upwards, like more users want to transact, then maybe you want to be strategic and you want to try and get ahead of other people. But otherwise, you don't really have an incentive to do that. And you find that once the base fee is stable, that's okay. Does it make sense? Yeah.
Yeah, makes sense.
Okay. So another simulation that I haven't published yet, I'm still working on it, is, so we often hear of this idea of next block inclusion. So in 1559, you can guarantee next block inclusion, which you cannot really guarantee now. In the current system, it's not really predictable when you will be included. You might have guesses, which are sometimes pretty good, but it's not always the case that you guess correctly. And so in this notebook, I try to find, well, if my users are learning over time, they're transacting many times with the gas market system, do they learn how long it takes for them to get in? And at the very beginning, my users have kind of random expected time to wait. So some of them think, oh, I'll wait 6 blocks. Some of them think I wait 12 blocks. But what I find is that once the users are transacting over and over, the ones that have high value, so value which is above, let's say, the stationary base fee level, these ones, they start to expect that they will be included in the next block, because they know that since the base fee is at this level, it's fine for them, they will be included. As long as you're willing to pay for the base fee, you will be included, unless the demand is shifting. And the ones who are not willing to pay enough, they start expecting longer and longer wait times. And here I set 30 as the bound, but you could see that in the end they will not get included. Okay, so either the users learn to expect this next block inclusion, or they don't value the transaction enough. Any question?
Yeah, not for me so far.
So the key is there's this next block inclusion.
Yeah.
Didn't exist before.
Yeah.
Let's say, yeah, but most of the time, and again, unless the demand is changing too fast, then you can expect to be included in the next block, because you know that by this time, the users who are not willing to pay the base fee, they're not going to compete with you. So if you are willing to pay for it, then you should get in, unless there's a big demand shift.
And this is something that you are currently working on, is that correct?
Correct. Yeah. I will publish it maybe in a few weeks. But yeah, wanted to show I think it's a nice, like, it really shows you that, yeah, you have this separation between users who are willing to pay and the ones who are not. And this is really the correct way to think about it. But after a while, you really separate. You make it like a very binary decision for the user. You say either you are willing to pay the base fee or you are not. Yeah.
That's it.
Oh.
Summarize.
So just
Yeah.
keep
Okay.
going.
All right.
Yeah.
Yeah.
So yeah, so maybe like to sum up this, The base fee is really what is operating this price discovery, so trying to equalize the supply and the demand. And in these normal conditions, when the demand is not moving too fast, when you don't have like a load of users coming in and happening, you really can get this behavior of users that are price takers. So they are quoted a price and they either take it or leave it, depending on how high they think the price is. And if you are a price taker and if you're willing to bid for that price, then you can also expect this next block inclusion at the same time, because you know that other users are not willing to pay the price. And when the demand shifts, so let's say you have Uniswap is launching their token or something like this, in that case, then yes, you have an incentive to be strategic, but it disappears pretty quickly once the price discovery is over. So there are some reasons to expect that these large demand shifts, they are infrequent enough. They don't happen too often. The base fee is quite quick to react and to reach the correct level. But even then, we could think about, let's say, wallet defaults that would make it easier for you to react whenever the demand is shifting. So whenever you have an incentive to be strategic again. I'm just going. I think I'm almost at time. Yeah.
Just one question.
Previous size. Previous slide.
How fast can the user learn to expect the next block inclusion? Is that like few blocks or like?
How fast?
Yeah.
So yeah, this is sort of it's a very theoretical. So the learning dynamics here, I kind of adapted them from learning dynamics, which are very common in game theory. So this idea that you try something and if it gives you a good result, you do that more often in the future. So it might not exactly translate to your actual real world experience, but what it shows is that this mechanism is kind of robust to users who are learning over time. So I wouldn't tell you that Yahsin is going to learn after 2 transactions that she can expect next block inclusion. But if it's possible for users to learn it over time, then that's what you should expect from the get-go. Like, you know that it's a property of the system that over time the users will learn and will expect this. Yeah.
Thank you.
I think that's clear. Right. Yeah, I'll just like finish quickly, but I just want to mention that so the transition period from the legacy system to the 1559 system will most likely be one where it's going to be like a soft transition. So the 2 types of transactions, so the legacy transaction where you quote your gas price and the 1559 transactions will kind of coexist, in the sense that whenever we receive a transaction that is in the legacy format, so where you're just giving your bid as the gas price, we're going to transform it into a 1559 style transaction where your gas price will be set to your max fee, because that's the most you're willing to pay. And then we'll reserve every part of your transaction, every amount of your bid is available for the miner to take. And depending, when the base fee is low, then of course you're giving a lot to the miner. When the base fee is high, maybe you're giving a little less. In either case, it's most likely better to switch to 1559, because whenever base fee is very low and you give this big bribe, maybe you could have gotten in with a much lower bribe. So it would be a better idea to switch to 1559 in that case. Yeah, does it make sense? But you'll still be able to send these legacy transactions for some time.
Yeah, that makes sense to me.
Good. All right. Yeah, and this is pretty much like a history dump. But let's say the genesis of 1559, Vitalik conceived of this idea in this blockchain resource pricing paper, formalized in 2019 into this EIP. There's a very long and very interesting Ethereum magician thread with a lot of debate and ideas and questions on 1559. When Vitalik came up with like what he calls a skinny 1559, which is a bit more easier to implement, and which is the model that I presented today. And since April of this year, we've had implementers calls usually once a month. They are available on YouTube. All the links are on this link, and it's very important trove of information, and the most let's say state-of-the-art things are there. And so what's next for 1559 is, well, on my end, on the robust incentives group, which also I'm working with Fred, who I think is watching. We are developing more simulations to investigate this transition period, which I explained a couple of slides ago. Looking at what we call the floating escalator. You might have heard of a competing proposal called the escalator. Floating escalator is combining 1559 with that. Looking at wallet defaults. So as I introduced, sometimes you want to be strategic, and in that case, you might want your wallet to help you make that decision and to help you set your strategy correctly. So this is like an important question. And also, how should clients handle the 1559 transactions? So these transaction pool policies. But that's, let's say, in my realm. I think the most important realm currently is really getting 1559 to the mainnet, which is, of course, the most important part. And the developers are actively working on this. Tim Bako is basically our project manager on this, and he's doing a fantastic work, like compiling notes on the calls and generally like pushing things ahead. He has a very nice mainnet readiness checklist, which you can see our progress and what we still have to do. We have currently like testnet, so proof of authority, kind of small testnet, not like a full-fledged testnet yet, but it's running with both Besu and Nevermind. And soon Geth will be there too, sending 1559 transactions to each other. As another important thing that I think is important, that this researcher, Tim Roughgarden, which is a very famous game theorist, is going to work on a report on miner incentives and 1559. So the security, how do you frame these fee market improvements in terms of game theory efficiency? I touch upon it a bit in some of the notebooks, but yeah, Tim is a very important figure, and it's we're really looking forward to the report. And yeah, and if you have any question, or if you are willing to contribute, or my DMs are open, and some of these people are as well. So yeah, thank you for listening, and thanks for having me again.
Thanks, Barnabé. Thanks for your sharing. Just wanted to like invite everyone to start asking questions below the comment below the live stream link on YouTube. And I wanted to invite CC if you have any questions that you want to ask Barnabé in terms of research, in terms of research or implementation work, or just personal, I don't know, any other things, maybe not directed to.
Can you share the robust incentive groups GitHub repo? Or yeah, I really like your the Jupyter notebooks.
Yeah, so I should point out that we have a library. So Fred and I have been working on agent-based library to simulate this fee market. So I'm putting the link here. It's kind of a offshoot, let's say, of the rig, but we do have a couple more resources on the rig repo, which I will share as well. And you'll find on the homepage of the first link, you will find links to the notebook, as well as a short summary of what each one of them is doing.
Oh, nice.
Yeah.
And also you use a tool called Cat, right?
Correct, yes. I haven't used it too much in these 1559 simulations, but it's a simulation tool in Python, which it's not exclusively for crypto economic proposal, but I think the genesis of this tool is really in these crypto communities. So some projects have been using it. It helps to kind of clearly define what the steps of your simulations are, like what is the state variables, how do agents in the simulation kind of interact with it. So here in this free market, for instance, the agents could be the users of the miners. So you typically define strategies. Like the idea is not to write down a scenario and say, okay, this is going to happen, that is going to happen. Like you write down how these users and these agents are thinking, and then you just let them run for some time, and you see what happens, and you look at the tape after. I think what's really nice in these simulations is it really gives you like an intuitive idea of the mechanics and kind of the space of things that can happen. For me, at least, they've helped me also even like write down formal arguments about this base fee, let's say, stabilizing. So it's quite yeah, I think it's an important work.
Should we take a look at any other questions coming from the audience?
Yeah. Let me check. No questions for now.
So if you have further questions, I'm talking to the audience right now. So yeah, I would like to see all of the questions on Twitter or on YouTube channel, or we do have a Facebook group that's more accessible for the Taiwanese audience, because Taiwanese tend to use more Facebook. But I'm the person behind the Twitter account. So I'd be happy to like connect you with Barnabé or with CC if you have further questions, and I'm sure they'll be happy to answer. So next up, I'm going to introduce CC Liang. So CC is going to be our next speaker. CC is a researcher and developer at Ethereum Foundation. So I think basically the two speakers are colleagues, correct? Yeah. So CC has a finance background, but he learned how to program by himself and enter this amazing blockchain space by 2016, I believe. And so he and a bunch of people and like engineers and developers started Taipei Ethereum meetup group in April 2016. And CC himself joined the research team at Ethereum Foundation by 2017. And right now he's been working closely with Barry Whitehead and all of his games. So today he's going to talk about gas golfing for modular exponentiation. And I'm going to switch this presentation. Take over.
Share now.
Share now. Okay, there you go.
Yes.
Okay. And then present. All right. So please join me in welcoming CC.
Thank you, Yahsin, for introduction. Wait, let me find to this and this. So hello. Thank you everyone for coming, and really happy to hear to share this little 2 weeks experience with some researchers, and we did a gas scalping for modular exponentiation. Let's get started. Yeah, so why I want to share this topic. So I'm currently working on the optimistic rollup called Hubble project with Barry Whitehead, Bob, and Honor. And then in this project, we need to use BLS signatures to reduce data to commit on chain. But to use BLS signatures, we need to verify the message that people signed. So the message was in the form of byte byte strings, and then we need to turn it into the points on the elliptic curves. So we need to do modular exponentiation on that. So yeah, this fun golfing project started like accidentally. We were on a chat group with owner Kobe and Barry, and owner was optimizing the BLS signatures. And then in another chat group, and Dankrat was asking, like anyone working on Solidity BLS stuff, and then we said, oh, we happen to working on a similar thing, but we had the efficiency and security issue on the modular exponentiation. And then Vitalik said, oh, wait, you don't have to call the precompile function. You can do modular multiplication, it's cheaper. And then I started implement something, and then get back to between the chat groups, and then the chat group had some feedback, and then we keep optimizing the Solidity code, and then we really bring the get host, and it's very fun. And then we and I post the result on Twitter. We also had more discussions for Proto and Alex and Maybe, and yeah, that's and my all the approaches we tried, I've been organized them into a single repo. It's under my name, and the repo name is modular exponentiation, mod_xp, and you can play it on the remix with me. So the mission here, the modular exponentiation is we took the arbitrary input x, and then we have we already known the exponent and the modulus beforehand, and we need to calculate the result of x to the power of b, and then mod n. And in Python, you write this built-in function. It's power, and put the base and the exponent and the modulus here, and you get the result. But even in Python, if you try to write it more human readable way, when you run this function, it freezes forever. Because v is a really huge number. It's I've written here in hex form, but it has 252 bits that could translate to a decimal with 75 zeros. So you are even it's small base like 3, and you raise it to a power of 75 zeros. Of trillions of numbers that will make your computer freeze forever. So usually the naive way to calculate the modular exponentiation, you have to call the precompile contract. It's called EIP 198. It's deployed on the main address type to specify the inputs of the base, exponent, and the modulus, and the length of the base, the length of in bytes, and length of exponent and length of modulus. And since we are using the 254, and the base, exponent, and modulus are all 32 bytes. So we provide the 6 inputs, and we store them to the memory. So you need to get the free memory position and then assign store these values to the memories, and you call the precompile contract with the memory position of the input start and the end position, and then you also provide the return values to the memory position, start position and end position, and then you look at result from that memory position, and then you get the precompile result that's that actually the precompile they actually sent to the, if you run Go Ethereum, the Go Ethereum has a specialized library that computes the marginal exponentiation super fast. So that's why we call it precompile contract. It's the real computation is not run in EVM. It's run in a library that implements on whatever client side you use. So how much does this compile cost? Cost 13,000. Yeah, we were so that's initially we were a little bit unhappy for that. We trying to optimize the result on this. So yeah, what can we do? So if we were to use a modular multiplication to replicate the modular exponentiation, we have this simple algorithm called square and multiply, because you don't want to just multiply the to the exponent that's super huge, that's like 75 zeros. But with square and multiplies, you can the steps to do it to compute is just like 252 bits of the exponents. So observe that if you have a number that's x to the power of y, and you take the square of this number, it's x to the power of y double. But if you multiply this number with extra x, you get the x to the power of y plus 1. And then if we represent this y as a binary, so squaring x to the power of exponent means you are shift the exponent left for 1 bit. And if you are multiplying additional x, that means you are adding 1 bit to the exponent. So we can implement this into Solidity. But before that, there are 2 ways you can do square multiply. You can send the exponent bit from the right and build the exponent from the right. So let's see, if you have the exponent 1101, and we have this accumulator called xx, and it is initialized as 1, and x is initialized as the input. So this is this column is the so xx is x to the exponent of 0. This is x to the power of 1. If we multiply x, we got 1, so the exponent is 1, and we square, we get the exponent of 10. This number is in binary. And then, so if we scan this exponent from the right, we got 1011. And if we got 1 bit, we do a multiply and a square. But if we made 0, we just do the square. And then you can see as if our 1011 is growing from the right to the left. growing from to the right to the left, the bits like growing, and then this is building exponent from the right, and we can build it on the left too. So we still have 1011 as exponent, and then if we scan it from the left, so if it's 1 bit, we need to do the square and multiply. If it's 0, we just square, and then we still you can see we're growing the 1101 from the left. So before we rewrite the code, let's do an estimation. So one module multiplication costs 8 gas, and square multiply needs 1.5 module multiplication per bit, because if it's 0 bits, you need a square. That's one multiplication, and if it's 1, you need a square and a multiply. So that's 2 multiplications. So our exponent v has 252 bits. So it's averagely you 1 bit needs 1.5 module multiplications. So you can calculate it's like 3,000 gas. It's all we really need. And then so yeah, we already beat the precompile. Yeah, thank you. That's my talk. Thank you very much. But no, we have to really implement the code. So here is the naive solidity. We just this is building the exponent from the right, and then we have this x initialized, and we have this modular and exponents and constants, and then we scan the 252 bits. We shift with I bits, and then we end it with number 1 and check if the shifted bit is 1. And then if it is, we need a multiplication, and if not, we just square it. And then so can we get the 3,000 on here? No. Oh my gosh, it's 38,000. Why? It's 10 times of the cost of the 13,000. How come? Can we have a way to improve that? So I learned this solidity assembly from Honor. So you can see the code looks like almost the same. We just wrap it with a stem bracket outside, and inside our for loops looks a little bit different, but it's almost the same. And we just write a different way of shift right. And can we like reduce the gas cost with this fancy way? We save 8,000 gas, but it's still far behind the 13,000. So I send the results to the chat group, and Vitalik said, "Oh, maybe we have too much overhead in the for loop, because when you loop 350 times, you need to like compare the I with another number, and then we need to add the I with another number. Those are overheads, and we are like looping 252 times. But if we like copy pasting our for loop body 4 times, and we reduce the for loop to the 63 iterations, then we might be able to save some gas. So, oh, it saves a lot, but it's still 23,000. It's still we are not beating the precompile yet. But what if we unroll more and like we copy pasting 8 lines in the for loop B and reduce the loop iteration to 31. No, it's not saving much. It's only one about 2,000 this time, saving 2,000 gas. What else can we do? So maybe because we did a lot of if statements check, what if we could remove those if statements, because the if statement use the jump I opcode, and each jump I costs 10 gas. So Vitalik has another trick that if we are checking the V and the 1 bits, and we are checking the bits and to determine if we need to multiply. I skip the square part. We just focus on the multiplication part. And then you can turn the if statement into this formula. You can see if V is 1 bit, and you get the XX assigned to XX multiply X. But if it's 0 bit, it's XX do nothing. So we rewrite our Solidity code and change all the if statements to this formula. It saves 100 gas. Okay, I think we are really pushing to the limit. And yeah, so at the end of this, I kind of a little bit giving up, because we've tried many things we can try, and then we watched this. What we have now is many lines of Ninja code. It's already unreadable for a human. But then wait, what if we just push this Ninja code to the limit and just try to be human unreadable and to the limit, and we just unroll everything, because we already know the exponent beforehand. So actually we can do this, like we write a Python code. It's a code generator. We scan the bits from the left to right, and we print. If the bit is 0, we print a square, and if the bit is 1, we print a square and multiplication. So we just print all the Solidity assembly line we need, and then we just like copy and pasting all the outputs of the Python code into the Solidity function body. So this is how it looks like. I omit some of the middle part. If you print out the whole code 252 maybe multiply 1.5 lines of those assembly code, it looks like the right, this bar on the right, and this bar is throwing up some gas there. So okay, so how could this code achieve? We achieved 7,000 gas. So that's half of the precompiled codes. So yeah, and I report this result to another chat group, and owner said, "Oh, that sounds interesting," and then we can try the addition method. So in double and add, we for example, if we want to double square and multiply, yeah, we want to multiply, but it's double and add on the export. If we want to double and add to the number 15, we need these steps. But with addition chain, you see there's one step saved. The step previous, first three steps are the same, but the at the end of the step of addition chain here, the addition chain reuse the cached 3 before. So what addition chain is? Addition chain is actually there are many algorithms to do that. It explores the explore addition path and give you given a constraint of how many storage you can use, and it finds a better path to do the addition and try to minimize the steps you need. So we can save more module multiplication this way. So Kobe Gurken used some smart way to do the addition chain, and then we brought down this gas code a little bit to the 6,700, and then even better, Proto Lambda, he observed the compiled bytecode, and he come up with even brilliant idea. So if we pass the monster code to the remix, and you observe you run the debugger, and you will find that it shows this repetitive patterns of the opcode, and that's if you want to do one module multiplication, it needs to arrange the stack so that you can get the right input for the module multiplication and calculate the next x value. So you can see that just by doing one module multiplication, you need to do 5 this duplicate and pop and swap. These are like costing 3 gas, but like they are one multiplication, and you get the extra like 15 gas for that. That's bad. That's not cheap. So Proto did this brilliant idea. What if we arrange the stack beforehand, and then we just run all the module multiplication without arranging the stack again. Yeah, we didn't have the movie Tenet on theater back then, but then I realized Proto's idea is a temporal pins attack. So first, we're not doing the scanning the exponent from the left, but first we need to on the right, and then we try to predict what would be at the end of the stack, what's the item in the stack we need. So if it's 1 bit, we need to prepare the value modulus and the value of input there. That's you need to multiply. And if it's square, you need to prepare the modulus there. And then after you do the reverse tricks here, and then we push the initial value, then we run all just duplications and module multiplication in a forward for run. And so you can see here for each one module multiplication, you just need 2 duplication there. So it's cheaper than the Solidity bytecode that Solidity compiled. So wow, that is amazing. It's achieved 5,000 gas. It's Proto running inverted. Yeah, so all in all, the root cause is EIP 198 is mispriced. it's like Vitalik defined maybe 5 years ago, and then after this 5 years, we have improvement in hardwares, in algorithms. So there are new EIP 2565 and 24.6, and they are they have a new gas pricing to make the gas price right. And Alex said on Twitter that I can give an estimate how if we run the precompile and with the new EIP as if they were online, if this is the number I get. If the option 2, I heard option 2 is pursued in the birthing upgrade, it's 8,400. So our cascading of course still work, and there's a great YouTube introduction by Kelly Olson of the EIP 2565. Yeah, so just give a summary of this. So what we have tried, we did an initial and estimate. We recognize quality and assembly. We unroll rules. We try to move if statements, and we use code generators. We unroll everything, and we try the addition chain, and we do a byte manipulations. Eventually, we use addition chain in our code base because I haven't figured out how to import the pure bytecode in Solidity that can be consumed by other Solidity functions. If you deploy the bytecode as separate libraries, then you need extra 700 external code to use those bytecodes. So yeah, addition chain is the low-hanging fruit we can get. It's my best fruit, right? My favorite food. Yeah, thank you so much.
CC, I'm going to invite Barnabé to come back and rejoin us because I believe Barnabé has a few questions for you. Before I invite Barnabé to ask his questions, I have a question coming from YouTube live stream link. And the question was, from Mingde Wang. He asked, what is gas golfing? Can you explain more about that?
Oh, right. So that name confused me a lot.
It confuses everyone. So it's a good question.
So okay, I looked up to the Wikipedia, and the gas golfing is actually from the cold golfing. But why is it called golfing? Because it's a sport that we are not trying to achieve higher score as possible, but it's a sport that we achieve as lower score as possible. So I think that's the original why the people use golfing for the code golfing, is trying to write efficient code for that, and then we named this gas golfing. So yeah, that's people used to code it.
Yeah, sure. So Barnabé, do you have any questions or comments that you would like to?
I mean, it was really nice presentation. Like I don't know any of this, but I could follow just by looking at the frogs going. So it was really nice. But no, I actually have like a question on the project that you are working on to use this modular exponentiation. So what kind of optimistic rollup is it? Can you share more?
What kind of optimistic rollups?
Yeah, let me let me share the link, or let me maybe next window. Oh, wait, let me. behind the Hubble.
So the project is called
The Hubble project, and the Chrome tab. Yeah. Can you? Oh, sorry.
I can see.
Okay, you can see. Nice.
Can everyone see?
So this is the optimistic rollup we are working on. It's still it's mainly smart contracts, but we are working on the node, and we are trying to do a soft launch on the mainnet soon. And we use BLS as signatures because we let the coordinator or let them commit a state root on chain, and also the transactions and the signatures. And then if the coordinator commit the wrong state root, we can run the proper function to dispute the state root and slash the coordinator. And because we have to verify those senders of the transaction are like the senders are signing their transactions, and we have to verify if their signatures are correct. And so we have to put all those signatures on chain. But if we use ECPSA, each 65 bytes, and there will be a lot of data to come in on chain. So we use the BLS signatures. So you use I think 64 bytes for all the transaction you have, and then it saves the data we need to come in on chain. Yeah.
Nice. Did you get inspired by Eth to use the BLS signature?
It's actually me. I think it's Barry who spec'd out the project. I think maybe it's people trying to try the BLS signature to do the optimistic rollup. I think it's maybe it's origin from Vitalik's idea like years ago.
A few years ago.
To aggregate the signature is easier.
Yeah? Do you mean aggregate signature?
When you have like many signatures and you're trying to aggregate them in a single verifiable signature?
Yes. Actually, the coordinator will aggregate signatures off-chain. So the coordinator are listening to people who send the transactions, and they when coordinator collect all the transactions, and they aggregate all the signatures, and they call the smart contract function to submit the aggregated signature. Yeah.
So I appreciate everyone's participation. I'm going to say a few words just to conclude the event. So yeah, thanks very much for Barnabé's time, and I appreciate your sharing. I appreciate CC's sharing. He also helped me set up the entire live stream broadcast, which is not an easy task. We are at this space called Block Squared, right? Yeah, so B2. So it's a new office co-working office space, and I appreciate Dr. Chang Chen. He very kindly let us use one of his conference rooms. He recently started this group in Taiwan called Untitled Labs. If you are interested in participating more events from Taipei Ethereum Meetup. So there's one coming up, I'm just going to say it right now. So it's November 5th, Thursday night, and it's going to be a physical event happening in Taipei City. We are using the Taipei Hackerspace event space that's close to Taipei Main Train Station. So it's Thursday night, 7 p.m., and we have two speakers. One is Hakka Finance founder and CEO Ping Chen. So Chen Ping, yeah. And then we have Oscar, who's the core developer of Eth Status Wallet and VAC peer-to-peer messaging stack. So these two speakers will be presenting their recent projects and ideas on the 5th of November. And another big event coming up is Crosslink. So last year we had Crosslink, drove some 300 developers and researchers in marketing and business and all these people around. And this year it's going to be pretty local because of the pandemic situation. But we still invite everyone who are in Taiwan, who will be visiting Taiwan, to participate. So it's 28th of November, Crosslink. So Fini Yang is one of the main organizers of this event. And if you want to attend, you want to sign up, be sure to follow our Twitter account. And if you're like mentoring speakers, you are welcome to join our Facebook group as well. So thanks for everyone. Thanks, Cici. Thanks, Barnabé. And I hope to see you on 5th of November. Bye-bye.
Bye.
Bye. Thank you, Barnabé.
Thank you, Barnabé.
Thank you.
Bye-bye.
Bye-bye.
Bye-bye.